Good morning. So for those of you who don't know me yet, my name is Ms. Stuckel. I'm sorry I couldn't be here the first few days of the trimester. I'm looking forward to seeing all of you later this week on Thursday. But since I'm not here to see your conversations or facilitate a board meeting, I wanted to take a few minutes to go over a few of the big ideas that I want you to get about the graphs for projectile motion based on what you've done so far. So I want to think about a projectile where you take something, you toss it out at an angle, so it goes up and away from you. So I want to start with the free body diagram. So like here's a sketch. We're going to start thinking about this projectile after it's left the person's hands and then while it's in the air. So once it's left that person's hands, there's only one interaction on that projectile as long as we assume that air resistance is negligible, which we saw at the end of try 2 with that where does the energy go lab. Air resistance is negligible on something like a bouncy ball. Now, that means the free body diagram has exactly one force on it. And that's the force of gravity, which is an interaction with the Earth. So now if I start thinking through my velocity time graphs. So first up, we're going to end up making 2 velocity time graphs for projectiles because we're thinking about these components of the motion separately. We're going to end up calling the side-to-side motion of a projectile the x direction and the up and down motion the y direction. So I'm going to start with that side-to-side or horizontal motion. And so I've labeled my graph with Vx instead of just V, where the x is indicating this is my velocity in the x direction. So if I go back to my free body diagram and I pay attention to just the horizontal, there are no horizontal forces acting on this projectile, which means that the forces on the horizontal forces on this projectile are balanced. As soon as you've got balanced forces, you have a constant velocity, which we figured out first trimester. A constant velocity is just a horizontal line on a velocity versus time graph. Now, just like we did earlier this year, I'm going to go ahead and annotate this. So the height of this graph, how far I go up the velocity axis, represents my Vx. Now you notice I just wrote Vx, I did not put a delta in front. That's because that velocity is constant and a delta is used to mean change. Now, the area of this graph, excuse me, is the distance traveled. So I'm going to go ahead and put a delta x because it's my change in position. And I'm using an x again to indicate that horizontal direction. Now, I can annotate one more thing on this graph, and that's the time, which is how far across this horizontal axis I need to go. And then I could even build equations based on this, like using the area, I can say delta x equals Vx times time. All right, so now I'm going to think about the vertical motion. So this, again, is horizontal. And now I'm going to think about my vertical or my up and down motion. And I'm going to label this with a Vy, where again that y indicates the vertical direction. Now, if I think about the up and down motion of that tennis ball as it leaves the person's hands, it is moving in the up and down direction when it's launched. And so I have to give it I have to give this graph a non-zero intercept. And I'm going to go ahead and label that intercept VIY for the initial velocity in the y direction. Now, if I think about as that tennis ball leaves my hand, it's going to start slowing down once it's in the air. So as it rises, it gets slower and slower and slower up until that highest point of its motion, where it reaches a velocity of 0. Now, at that highest point, it turns around and goes in the other direction. So to show it going in the other direction, I have to have that velocity go from positive to negative. And then it picks up speed as it falls. Now, another thing I'm going to go ahead and annotate on here is my final y velocity. And then I can go ahead and add delta vy. And again, the reason I put a delta in front is to indicate change. That velocity changes as the tennis ball flies through the air. Now, how far across horizontally? That still represents the time. And I do have to go all the way across this bow tie. And then the area still represents the distance traveled, but I need to get this entire area. And I'm going to label this delta y for my change in vertical position. Now, the last piece I still need to annotate is the acceleration, which is given by the slope. Now, I want to talk a little bit about the value of that acceleration. When you did your video analysis, you should have gotten a slope right around 10 meters per second squared. So the reason for that, when the only force acting on that tennis ball is the force of gravity, that means that the net force equals the force of gravity. Now, if I go back to my green sheet under force on a particle model, we figured out that F net equals ma. So I'm just going to do a little substitution here. Instead of F net, I'm writing ma. And then force of gravity is m times g, where that g is 10 newtons per kilogram. Now, because this mass and this mass are the same thing, I'm going to have my acceleration equals g. Now, if you look near the top under constants on your green formula sheet, has g equals 10 newtons per kilogram. So that means my acceleration is 10 newtons per kilogram. But it also has ag equals 10 meters per second squared. So if I take a quick look at the units, a newton per kilogram I can change into something else, because a kilogram, or a newton, is also a kilogram times a meter per second squared. So then if I have a newton per kilogram, these kilograms cancel, and I get that a newton per kilogram is equivalent to a meter per second squared. So what I'm getting at is that this ag, this 10 meters per second squared, is really just another way of thinking about the g that we've dealt with so far this year. It's just that depending on what on how you're thinking about it, sometimes newtons per kilogram is a more useful unit, and sometimes meter per second squared is a more useful unit. And we're getting to the point where the meter per second squared is a more useful unit. So I can go ahead and add to my annotation that this slope is not just the acceleration, but that the acceleration is 10 meters per second squared. So what we're going to be focusing on the rest of this week is sketching these graphs and annotating them and just thinking through what's going on in a projectile motion scenario so that we can set ourselves up to next week start doing a lot more with building these equations and doing the math for certain kinds of projectiles. All right, so I'm looking forward to seeing all of you on Thursday, and I hope you have a good week in the meantime.